Hello teammates, it's Mr. Nanini. We're going to look at Kepler's third law of planetary motion. I'm going to attempt to do this in one take. I'm going to run a little behind today. It's alright. So Kepler comes along and he ends up working for this cat called Tycho Brahe. And Tycho has been collecting data with what's called naked eye observation. They've got devices to measure the motion of planets and stars, but they don't. This is before the telescope. And Tycho's been collecting this data, and he gives Kepler comes along, and he gives Kepler a job because Kepler's right on his heels. Tycho realizes there's a pattern, but he can't quite figure it out. So he gives Kepler this mission to figure out the orbit of Mars. It was kind of anomalous, and it was very fortuitous for Kepler because Mars has the most elliptical orbit of the true planets in our solar system. The other planets have more of a circular orbit, and if we have time we can talk about that. Very unusual. And it probably has to do with the motion of planets early in the creation of the solar system. But most planets, and we observe now planets around other stars, have got a much more elliptical orbit. So anyway, Kepler looks at this, and again, Tycho just gave him this to try to get him out of the way. And so Kepler discovers this. I'm going to try and do this in one take with my field expedient drawer of ellipses. We got two foci, and you did this in geometry class, I bet. I hope. And we know the sum of the distances, whoops, like I said, we're going to do it in one take. The sum of the distances don't change. And that gives you that elliptical orbit. So in our solar system, imagine this being the sun, and this being the orbit of Mars. It's elliptical. Now I was asked a question, well, what's at the other foci? Nothing. It's just the way the geometry works out. It's the interplay with, and it's a fascinating study. It's an interplay between the force of gravity, and as you saw in the videos, and you know, right, the closer you are, so here's Mars. When it's closer to the sun, here's Mars. When it's further from the sun, and you know that the force of gravity here, when it's closer, is greater than when it's further away. That pesky inverse square law. And so the force of gravity is greater, and that gives it a greater velocity through that whole centripetal force concept. And even though Mars isn't moving in a circle, we can describe, if you those calculators amongst you, we can get this down to the limits where we can describe the very small motions of Mars as circular motion. So that interplay, and you've got that tied with the conservation of angular momentum. And so we can treat Mars as a point object. It's moving in relation to a rotation pattern. So we can also talk about angular momentum is conserved. That angular momentum is preserved from the creation of our solar system. So when the solar system formed, when that dust and gas started to attract, it started to rotate. It's a fascinating study on how we think that happened. But everything wasn't just rushing right to the center. Some things apparently were off-center a little bit, and that causes rotation. That's why all the planets rotate in the same direction. And that angular momentum from the creation of our solar system is what keeps planets in their motion today. Now, Kepler came along before Newton. He presaged Newton by about 80 years. Interestingly, all I've read and what science historians have expressed to me as I've read their works, oddly, Newton never really gave Kepler credit. It's clear he based a lot of his thought on what Kepler had developed. Very odd, even for Newton. Because Newton, although he hated Hooke vehemently, he was usually pretty generous in identifying the works of others. Interesting on Kepler. Let's look at the problem from yesterday. So I gave you a problem. I gave you a period of t equals 50 seconds. I gave you a semi-major axis of 2 times 10 to the 6 meters. Now you saw in the video the discussion on astronomical units. Those are really left over from back when we didn't have a good way to determine the distance between celestial objects. You'll still run into astronomical units a little bit. It's really, as time goes by, it's falling further and further away from being used. So we're going to use meters here. So you know my super first, third, and seventh hours know that we always got to convert. Oh, these are days. I'm sorry, days. I gave you meters. Always physics. All the equations are written in standard units of meters, seconds, and kilograms. Your first step pretty much with any physics problem. So we want to get days into seconds, easy money. We know that there's 24 hours in one day. We know that there's 60 minutes in 1 hour. We know that there's 60 seconds in 1 minute. Days cancel, hours cancel, minutes cancel. Leaves us with seconds. And I calculate, I round it a little bit, 4.32 times 10 to the 6th seconds. And we wanted to determine the mass of this object, this, and again, you can call a moon, anything that's going around something else, we can call a satellite in astronomy. So we gotta know what the satellite is. The mass of the planet that the satellite's orbiting. We're gonna write Kepler's third law, because I want to make a couple points here. Semi-major axis cubed. When you look here, 4 pi squared, only the pi is squared. So it's really like this, and I'm not sure, it's the way the equation's written. It's really like that, and that kind of looks familiar, doesn't it? The second thing is you can ignore, and like we did with the example yesterday, as long as the star or the planet is much larger than the satellite, we can ignore the mass of that satellite, and that's what we're going to do. It drops out. It's trivial, as they say in math talk. I'm going to rearrange to solve for mass. Mass, I'm just keep on calling mass 1, equals 4 pi squared over big G times period squared times semi-major axis cubed. And there we go. So now coming back to here, be careful when you come here. It's not 4 pi squared. It's pi squared times 4. So just watch that. When I do this, I've got a little, I just keep it in my head. It's about 39.47, 39.45, and I just keep that in my head, and I don't got to squirrel with that. So let's solve this. Let's solve this, and we're going to get 6.67 times 10 to the minus 11. I'm going to drop units just to speed up. 4.32 times 10 to the 6th seconds. Don't forget to square that. All this times 2 times 10 to the 6 meters cubed. And you should get, and check me out if I get this wrong, somebody send me a note. I think it's good. 2.53 times 10 to the 17th kilogram. That sounds okay. That sounds okay. All right. Let's do one more. This is new. So this is the plan. This is the plan from yesterday. Let's do this. So let's say I've got a star. It's got a mass of 2 times 10 to the 30th kilograms. It's got a satellite, a planet going around it that's 5.98 times 10 to the 24th kilograms. It's got a semi-major axis of 1.5 times 10 to the 11th meters. And we want to figure out the period of this planet going around. So we're gonna solve for period, and I want to show you this because you're gonna see this in your careers as well. I'm going to rearrange this again. It's the mass that the planet is going around that matters. Oh, no. I want the mass. Mass of the star. And you're going to see this. If you see this notation, r to the 3/2 power, here's what's going on. And you'll notice I'm solving for t. So my 4 pi squared square root becomes 2 pi, doesn't it? And that's what's happened there. I'm taking the square root in my denominator. And then I'm taking my semi-major axis, 1.5 times 10 to the 11th meters to the 3/2 power. Same thing if I'm taking the square root of something to the 3rd power. I'm gonna get 3/2. Yeah. That's a little algebra. I think that's algebra refresher. So you may see, in your careers, you may see this. T is proportional to R to the 3/2 power. That's Kepler's 3rd law. Sometimes you'll see this called a proportionality constant. I don't use that term because it's really not a constant, is it? It's 2 pi over the square root of big G, but times the mass of your star, your planet, the satellite's going around. And that to me is really not a constant. But you may see it referred to that. That's why. The reason I tell you all this, because I armor you up so you can go forth and solve. And teammates, I want you to give this a shot. I want you to solve this for period. I want you to get a calculator practice. I got 1.98 times 10 to the 8 seconds. And I'm pretty sure that that's it. Because what I gave you was, I gave you the mass of the star is the mass of our sun. That's the Earth's mass. It drops out. It doesn't matter. That's the average distance between the Earth and sun. Earth's orbit's kind of elliptical. But you should get that. And when you boil that down to days, you're going to get 365 days. Teammates, send me a note if you got any questions. We're out of time.